Okay, I'll give you some intro on the IEC Common Information Model. That's the common information model for the electric power sector. There are other common information models in some other sectors. Well, let's get started. Okay, what is the IEC CIM? Well, basically, it's an RDF model that's made for the electric power sector, mostly for the NSOE and other load flow calculations primarily, but has since expanded very much into other business processes and other use cases in the electric sector. But the main driver was basically the load flow in the NSOE network that needs to be done between 40 TSOs, that all of them need to submit a part of the entire European model, then it all has to be connected, and then the calculations can be started. Okay, but what makes the common information model? Okay, the basic part is the model. That's the data dictionary, I would call it. So this is a list of classes and attributes with semantics. So this is a transformer, it has these parameters in which mean this and that, and this is done by the domain experts. And it's done in Enterprise Architect. Basically, an UML diagram is drawn with relations between these objects. And it has since expanded. It has a few thousand classes now, I think, this basic dictionary. And then from this dictionary, there are profiles being made for specific use cases. These are the profiles. So a profile is a selection of classes and attributes for a specific use case. And there's the serialization part. So the standard defines a few ways to serialize this model data into a file, basically. So the most common serialization is CIM XML, which is basically RDF XML with some, for now, incompatible changes, because the standardization was not, for RDF XML was not ready when the CIM XML was made, so some errors were made. So for now, it's not completely compatible, but it's mostly RDF XML. And there are other serializations. There will be JSON LD is now being standardized. And there's the turtle serialization, which is a master model, but it's not really used in practice. So basically in practice, when we're talking about the commercial tools and software, you have CIM XML for the serialization. Okay, so it's a set of open standards for representing power system data components, basically mostly network models. And these are three basic use cases. So the most important use case for us is the network model and case data exchange between control centers, and that's what we in KONCAR deal with mostly. There are use cases for electrical markets, energy markets, which we are not really dealing with in KONCAR and not know a lot about it. And there's some, so you can use the CIM dictionary for exchange of models. That's basically a CRUD, create, update, delete. You're synchronizing two databases of network models. You can use it for markets, so basically exchanging some market data, nominations, etc. So some small time series mostly. And you can use it for messaging. So you can construct some REST API, XML, whatever messages for communicating directly between, I don't know, workforce management systems, etc., but which need to refer to the basic network model. So you're sending an, I don't know, worker to repair some component of the system, and the component to be repaired is referred to the CIM model. But you're using CIM not to exchange models, but to exchange some orders or whatever between two systems. For example, workforce management, SAP, or enterprise resource planning, whatever. These are mostly these more business-oriented systems. And what does the common information model, the CIM, define? It only defines the semantics and the data exchange. It doesn't define how you store the data. It doesn't define how do you manipulate the data. So these are all application level concerns, but the standard is not dealing with it. So it's not a complete solution as in a silver bullet. You can use the standard to exchange data between applications, but how do you deal with it in the application is up to you. And how do you store it, most importantly, which is a issue that we've tried to address with our Power CIM model manager, the storage of the model and querying of the models. Okay, the standard is developed by IEC Technical Committee 57 with few working groups. There are working groups for market and working groups for transmission and distribution. And this link, CIM user group, this is the main link that you can use to, I don't know, get the real files, the schemas, and etc. about the standard. Okay, so as I said before, CIM uses an UML ontology to define the basic dictionary. So it defines some classes, some attributes, and relations with multiplicity. It uses only single class inheritance. For identifiers now in newer versions on UUID, a 128-bit identifier is mandatory. Before, you could use something else too. And what is very important, you can extend the standard because, I mean, 95% of the standard is okay for some use case, but every DSO has some data that needs to be added. So the standard can be extended. You can add classes, you can add attributes to existing classes, you can make your own profiles, etc. But the basic data is RDF data, so it's triplets. You have some class instance defined by the ID, you have some attribute, and you have a value attached to that attribute. But in practice, you mostly deal with it at the object level, not at the attribute, at the single triplet level. You mostly deal with objects at the object level. So you want one object that has an ID and has many attributes inside. Okay, and the way you do, there are many ways to do some syntax and semantic checks. Some of them are deprecated, like OWL and OCL. Now shackle is used, and that's on the high level. And the highest level, of course, is application validation. You need to load the data in some application and try to do some calculation, load, flow, whatever. On the lowest level, you check XML validity, XSD schemas. You have RDFS schemas, but most of these low-level checks are not expressive enough to make all the checks necessary. With multiplicity, with relations, there are complex relations that you need to check that the model is okay. And these are mostly done with shackle rules. Okay, so shackle rules are part of the standard. Shackle validation rules are part of the standard. They're still not complete, but they can be used to validate a model before you put it in some application. But still, application testing is necessary because all of this validation is not enough to check if the data is really good for a big network. Okay, last time we had a SIM meeting like this when I presented. We were presenting PowerSIM, but there was a misconception about terminology. In KONCAR, we come from the SCADA world. So for us, data is measurements. Data is time series samples. That's what we mean when we say data. And the SIM model data, that's a network model, the model of our network. So we call it model shortly. And when you have the SIM information model, which describes your network, okay, then it's a meta model for us shortly. These are not really official terms, but you can find it around, people shortening it and using it like this. And we have some header data, okay, we call it metadata. But back, I mean, some of you are from the knowledge graph, whatever world, ontology world. Therefore, you RDF object data is the data. That's the primary data you're dealing with. And some UML RDFS definitions are the model. And this was a terminology misconception last time. So for us, primary data is measurements. For somebody dealing only with the models, primary data could be object data, RDF data. But for us, that's model, and the SIM information model is a meta model. Okay, but it will be all clear from the presentation. Okay, and the SIM model, some say it's object-oriented. Okay, yeah, you have objects, you have classes, you have instances. But the model can be reinterpreted as a relational model because you have relations, definitely. It can be interpreted as a document model because each object instance is basically a mini document with, I don't know, 10, 20 attributes. And okay, so it's electrical network, so basically it's a graph. So it can be a graph model. So, but basically you have a list of objects and attributes. Some of these attributes are links to other objects. And every instance has its class and a unique identifier. And these objects can be whatever, can be physical elements, can be some organizational elements, containers, some just topological elements that define connectivities, or types. You have transformer type, whatever that you use. You have 20 transformers of a type. And then an object instance is the type that holds the parameters. And you have all of these other GIS data or diagram data, etc., that has been added to CIM. The basic classes and attributes are prescribed by the standard. But of course, you can extend the CIM with custom classes, attributes, etc. But what's important, some of you say, okay, it's a graph, it's a triplet model. We just load it into some triplet database and we're done with it. Yeah, but it's pretty big. The models can get pretty big because you have tens of thousands of elements. European network, I think, is gigabytes. So all of these tools are not basically meant to handle this much data, and all of these tooling that you supposedly have, in practice, you're writing your own XML, not parser, but you're using an XML library, you're using Jena for shackle validation, but it's slow. So yeah. Okay, and the CIM serialization that we got into now, it's a standardized rendering of RDF data into some files. So basically, these are the three types. But CIM XML is used. JSON LD is in standardization now. And some of these attributes represent relations. Other attributes are just parameters. And unfortunately, CIM XML is not completely compatible. Some of the tools can be used, but there are some incompatibilities. And there's some misuse, I would say, of RDF features, like RDF about, RDF. You have these RDF features that you used for some use case in the CIM serialization that's not really good. And the problem basically is CIM is in development for a long time. It has been used not for the entire, but it has been used for years now in control centers, and this software and the processes in NSOE are very slow to upgrade. You need to get all 40 TSOs to upgrade their software. You need to have interoperability meetings to check if everything is working correctly. So once you deploy an old version with some problems, it takes a long really to upgrade everybody to the new version. So for example, serialization, you had headers that were encoded separately, basically not like an RDF object. For now it has, it will be extended, it will be harmonized with DCAT, but still the headers will need to be an extended DCAT header because there are some features that DCAT doesn't have. DCAT is meant for like a catalog of data, but here we have more like updates to a model. You need to have referring models. This is more like a version control software thing that is not, DCAT doesn't deal with stuff like that. And you have the CIM data types. So CIM has its own primitive data types, which basically correspond to XML types, but now need to be harmonized with JSON types. And sometimes the serialization, I mean, it has some flaws, especially with complex data types, but it's solvable. Okay, so, and CIM profiles. A profile is a subset of the model, so a list of classes and attributes for some use case. The transmission standard 61970 uses RDFS, and the distribution and market standards use XSD for their basic schemas. But then you have additional constraints, which are, some of them are coded in natural language because nobody wrote some shackle or whatever, or cannot write to check a condition like that. And then you have profiles. The basic profile is equipment and topology for us. Then you have the load flow for the load flow use cases. You have geographic and diagram layouts for geographic diagram data, dynamics, etc. But these are the basic profiles that are mostly used by everybody. And this is a little picture of the, so this is the TSO, transmission standard, that's oriented towards network model exchange, mostly for the NSOE. And there you have the network model for EMS calculations, load flow, short circuit, etc. Some for the dynamic. And the big part of this, you need to merge all the 14 models. So a big part of the efforts are oriented towards this business process. You need to merge the models every day so you can do the day ahead congestion, forecast, calculations, etc. You need to handle all the 40 TSOs and need to join their networks on the boundaries, which are borders. You have like border elements, which are the elements in which these networks join. Okay, and this is the distribution standard. We call it distribution standard, but it's more oriented towards business processes and integration of third-party applications, software systems, whatever. So you have the workforce management, asset management, distributed energy, because the distribution deals with a lot more entities other than, TSOs deal mostly with other TSOs and their own DSOs. DSOs deal with customers, deal with distributed generation much more, etc. More maintenance, metering, etc. So this standard, this working group handles this. And there's the market working group that I don't know much about really. But why CIM? I mean, CIM is a model. Whenever you make an application, you have an implicit, some sort of common information model. But someone has come before you, has invested many engineering years of domain expertise to make a model like this that you can lean upon, that you can use to make your own applications. So now CIM is really unavoidable in the electric sector, at least in grid level operations. And what it enables you to interoperate with various software, be it SCADA systems, some standalone modeling software like PSSE, NetPlan, whatever. GIS systems have exports to CIM, some market systems, workforce, etc. Asset management systems like Hitachi's or Oracle's all have CIM, at least CIM compatible internal data models and some CIM adapters so they can pull in or export data to CIM. And of course, if you're in Europe and you're a TSO, you have mandatory integrations with NSOE that need to be done to CIM. So basically, you have a model that's done by domain experts. You have a standard, so you can reduce the effort hopefully reduce the effort by using a standard. And you can reduce those point-to-point connections between applications. You can have more of central systems for handling model data and standardized adapters between systems. Okay, some CIM concepts. So you have the identified object class. It's a base class for all objects that have names. And these are most objects, at least, that we're interested in. And the identified object, so every object has a basic ID, UID, and it can have multiple names in other contexts. So in GIS, it can be called like this. In, I don't know, SCADA, it's called like this, but it has a UID in CIM, and that's its primary identifier. Okay, the concept of inheritance is really cool and necessary because you have objects. For example, the breaker is a common example. So a breaker is a switch that can break on load, it can break current. The breaker is a switch. Switch is conducting equipment, as is transformers are conducting equipment, lines are conducting equipment. So anything that has wires that carries current is conducting equipment. Then you have equipment that includes some equipment that's not conducting, I guess. I don't know what goes into that really. Then you have power system research that we'll see later. And all of this is unidentified objects. So this inheritance, I don't know, it grants you object orientation and the ability to define characteristics on a level that's good for you. So you define names on the identified object, you define specific attributes on the breaker switch level, etc. A core part of CIM is these container classes. So you have classes that are not physical, that don't have any parameters, don't have any physical parameters, but these are just used for containers, for organizations. So you have regions, substations, voltage levels that contain your relations other objects and that you can get use to get a hierarchical representation of the system, to get some sort of organization in the data. And this is really important. That's the PSR, so power system resource. This concept in CIM, it enables you to correctly model assets separate from functions, because you have a place in the network, for example, for a 110 kV transformer. But this place in substation, whatever, ABC, that's different from the specific transformer that is now installed there. Because, I don't know, tomorrow this transformer might burn up and you will replace it with a new transformer, new serial number, but it will have the same functional role. So the functional role is the power system resource. That's the element in the network. But you have an asset class, asset object, that's a specific transformer with specific serial number that can be in storage or can be in the network connected, whatever. And you have asset info, that's a type nameplate. For example, when you have many units with common characteristics, then you have a single asset info class that you refer to as a nameplate for all of these elements. What are more concepts? For example, you have headers, that's metadata, who created this file, when has it been created, whatever. Important part is the superseded by, so it refers to the model that it replaces or augments. So it's even a complete model, a complete export, a complete file, it has its own UID. So you can refer to the model itself, not to the classes inside the model. You can refer to the model, to the complete model. Okay, you have diagrams and geographic data. Diagrams enable you to encode single line diagrams mostly. So these are these SCADA pictures, and to exchange it between systems. And this is vendor neutral. It only defines locations of symbols and lines, and every application can style them according to its styling rules that it has. And geographic data, it's a relatively simple implementation, but it enables you to encode basic GIS shape objects. You can have points for locations, line strings for lines, polygons, for example, for substation, boundaries or regional boundaries, whatever, and you can attach it to objects. This is not a replacement for a full GIS system, but it can be good so you can exchange these geographic pictures, mostly for presentation on the SCADA. An important part of CIM it deals with is the network topology, network connectivity. So all conducting equipment classes have their terminals. The terminals are like places where you can connect these elements to a connectivity node. So only terminals can be connected to a connectivity node. Connectivity node is a node. For example, a bus bar, whatever, some equipotential part of the network. And then in CIM serialization, you have all of these objects separately. But the references that these terminals, connectivity nodes have, they connect each other. And that's the way you can encode an entire network topology, be it node breaker or bus branch, whatever. So full topology or condensed topology, you can encode it in CIM, and you can import it to various modeling software. This is really the basics of CIM. Okay. All of these connectivity nodes and terminals, they can handle phase relationships too. So you can have a connectivity node that only has 3 phases. You can have a connectivity node that has 3 phases plus neutral, whatever. So this thing has been modeled really good. So you can have multi-phase network. You can have like single line diagrams, 3-phase networks, or you can deal with phases on their own. For example, if you have unbalanced networks in distribution, then you need to handle the entire network, not 3-phase, but single phase. Okay. Okay. This is the CIM modeling part. Done. Now, difference model. So when you have these control centers and INSOE exchanging models, you don't want to send the entire model every time, maybe because it's big, but it's not that important. What is important is that you can see which changes have been done. So you just ship the changes. And this is supported on CIM in a way using the CIM difference model. So basically, it's incremental data exchange of model changes. You can create objects, you can delete objects, or you can update some of these objects. And the way it's encoded is a bit strange for us software engineers, because instead of explicit create, update, delete annotations, so you know which operation it is requested, they use some forward and reverse differences. So you have two lists of objects, forwards and reverse. These are supposed to be like forward diff. You have two versions, version 1, version 2. The forward difference should get you from version 1 to version 2. The reverse difference should get you from version 2 model back to version 1. So these encode the changes. Forward encodes the changes being done from version 1 to version 2, reverse the reverse changes. But in practice, you need both, always need both to get which elements have been really deleted, which have been created. So basically, it's a way to encode the create, update, and delete operations, but in a split way. But all of the CIM software supports this. So you can have a base model and many different models that you just attach like changes to that model. You can have multiple differences. So you have one base model and maybe 5 alternatives. And then you use the base model plus one alternative, make one calculation, plus the second alternative, you make another. So it's important for flexibility of work with models. And the CGMS, okay, CGMS, you have the CIM. CIM is a basic model, but it's not used directly in practice. NSOE standardized its own profiles using the basic CIM standard. And this is the CGMS. So it's a CIM profile done by NSOE for TSO data exchange in Europe. Now, CGMS version 2.4 is in use. That's basically CIM version 16 plus some profiles. Version 3.0 is standardized, but it's still not implemented because the TSOs are slow and they have a lot more problems. And these are the standards that NSOE has referred to for the profiles. It's mandatory in Europe, and it enables model exchange between TSOs or between applications within the same TSO. Okay, and these applications are whatever: data management, model management, load flow, short circuit calculations, congestion management. We are really important day-ahead congestion forecast and load flows, or for planning. Somebody uses today's network and then tests, task calculations, building new lines or whatever. And this is some diagram of the profiles used and the exchanges being done with CGMS. So CGMS handles most of this, but the equipment profile is the most important. That's what's being exchanged for now. The diagram layout is not really being used in NSOE right now, for example, but all of the others are really and used every day. Okay, and here's a short developer perspective, because I'm a software developer and I was in some CIM working groups, but not really an active member. And these groups it's designed by committee, basically. You have many vendors, many big vendors. They all pull in their own ways. They need a lot of time to make a standard complete. And these people are not electrical engineers. They are not professional software engineers. They're mostly electrical engineers. So there's a lot of, I would say, not really bad modeling, but there's a lot of things that could be improved. But still, it's a gigantic effort and really unavoidable today. The core idea is, of course, very good. I mean, I want to use a standardized model with my application. But it doesn't solve, as I said before, it doesn't solve the problem of your data structures, or how do you manipulate the data for your calculations, whatever you need, or database storage. And there's, of course, lots of minor problems. You have the slow adoption designed by committee. It's really a complex standard. You have a standard, but in practice, you always have problems with files. It won't import. So you manually edit the file to make it import. You make some tools, etc. The tooling is really not complete. They use many, like cool semantic web standards that should give us tooling that's really good, but you have some open source libraries and it's not really usable for what is needed today. Okay, you have Enterprise Architect, but that's a glorified drawing tool for UML. But when you get to creating the profiles, the schemas, to manipulating the data, to parsing these big files that are gigabyte size, manipulating the data, then the tooling falls a bit short, I would say. And a history that the CIM working groups had, they take an established standard like RDF and then make some sort of bad implementation on top or even incompatible. And then a few years later, it needs to be revised. And there are, of course, other problems, more domain-oriented. So you have the CGMS 2 and 3 transition that TSOs are really slow with. You have the headers, DCAT, problems with headers, problems with naming, the OCL that should be used, the OCL OWL validation, but now it has been deprecated and we have switched to Shackle. We have problems with complex data types and measurement units because of the measurement units have not been included with every value. Basically, so you need to consult a schema to know which measurement units your file uses. And that for me is not good because you should be able to do basic parsing without using an external schema or file of some sort. You should be able to read the file and say, okay, this is 11 megawatts without using an external schema. Okay, this is 11 and I need to add megawatts. And you have problems with these prefixes, namespaces that have been taken from web technologies and co-opted into, I don't know, okay, you need namespaces because then so you define something in their own namespace. This TSO defines some objects in their own namespace. But as I said, these people are not professional software engineers, and these standards that they've used, like RDF, etc., are also very complex. And adding all of this complexity doesn't always fit really well. But I mean, it's usable. The way it's still a lingua franca, you have a common language, and that's what is important. And as I said, good CIM tooling, especially open source libraries, is missing. So basically, you have all of these standards, but you're using a basic XML library to parse or generate XML, and all of the rest of the stuff you're doing on your own. You're using a basic database because all of these object graph databases, they cannot do what you need to do in practice, and they're not performant enough. You have modeling errors with transformers, modeling errors with names that will be changed, but it's still breaking changes and they will be applied slowly. You have weird object granularity. For example, they defined a position point as a standalone object. That's a point in for example, you have a line that's going for 100 kilometers and it has 1,000 points in geographic points. And every of these points is an object with an ID. Why would I have an ID on a coordinate? Why would I change a single coordinate? That's not how all of these other GIS systems, etc., work. If something changes on the line, an entire shape, an entire line string will be re-imported. So you have these simple errors, but which take a lot of developer time to, I would say, to correct. But still, I say CIM is unavoidable. It's really good that we have a standard that we can exchange data between applications. So, but it needs work, like all of these efforts.